My name is Brian Cunningham. I'm based out of Vancouver, BC. I've been with ELPRO for about 10 years now, and I've been in the industrial wireless space for about 20 years altogether. And although I kind of alluded to it in our previous session, I've been in the instrumentation and process control world for over 25 years now, working for several different manufacturers over the years as well. I started off working for a distributor here in Vancouver many years ago. So today we're going to talk about wireless concepts or RF basics. So we're going to talk about antennas and propagation and what to look for when you get onto a job site and you're thinking about installing a couple of radios. What are the things to be aware of? What are best practices and that sort of thing. So first, just a quick note about ELPRO here. The company was founded back in 1983 by a couple of RF engineers, and they built it up into a very successful company. And as you can see in the timeline there, around the year 2007, they reached retirement age, and so sold the company to MTL Instruments. MTL was bought by Cooper Busman in 2010. Then Eaton was purchased by Cooper Busman in 2012. Oh, I'm sorry, the other way around. Cooper Busman was purchased by Eaton in 2012. And then more recently, ELPRO was sold to an Australian company called Aquamonics, which is a manufacturer of flow meters and irrigation control equipment. Okay, so we're just going to jump in here. I did want to mention that we are recording this session, so if I could ask you to all please mute your microphones so any coughs or sneezes are not recorded for all of eternity. So with that said, we will just carry on here. These are the major industries that ELPRO products are used in. We do a fair bit in mining applications. We do a little bit with electrical power utilities. We do a lot with oil and gas. That often depends upon the price of oil at the time. And then we do a little bit with agriculture, and that's going to be a growing field for us with the irrigation products that we'll be looking at with Aquamonics. And probably one of the largest industries for us is water, wastewater. We have literally tens of thousands, or maybe even, I'm not quite sure on the exact numbers, but I would say well over 100,000 radios installed in sewage treatment plants, in lift stations, pump stations, water towers, all over the country. The other industries that we spend a little bit of time on, automation, traffic and safety, and SCADA. Virtually all SCADA systems use radios these days, so that's, of course, we're quite heavily involved in that. Okay, so ELPRO has quite an extensive R&D team located in Brisbane, Australia. And they had developed, they were first to release quite a number of new products here. And one of them was a peer-to-peer industrial wireless networking system. And they were the first ones to come out with that, so that the master radio no longer had to control all communications. A remote site could transmit directly to another remote site. We were the first to come out with a 1 watt, 900 megahertz self-healing, self-organizing mesh network. There's other companies that have come out with mesh networks at different frequencies, but none of them at the time we had done so had come out with a long-range 900 megahertz 1 watt system. And of course, there's numerous developments. I could go on and on about this. One of the things is we do own quite a few patents for our inventions over the years. They are registered in Canada, the US, and Australia, as far as I know. And of course, all of these radios are industrial grade, and that means that virtually all of them have Class 1 Division 2 approval, CSA and UL. And temperature ratings, -40 to 140 degrees Fahrenheit, so these can be mounted and installed outdoors. And of course, FCC compliant, as all radios have to be, ATEX certification, CE for Europe, AES for encryption, that sort of thing. So we're certainly very familiar with getting these products to meet certain standards in different countries. Here's what the portfolio of radios looks like, and here's how we break it down. I'm not going to spend too much time on this because we're going to be talking about antennas and radio propagation and things like that. But on the top row, these are the radios that have 4 to 20 milliamp inputs and outputs. The middle row are gateway type radios that have the ability to communicate using a protocol like Modbus or DF1 or Allen Bradley's Ethernet IP, etc. The third row are Ethernet pass-through modems. So all of these radios on the third row, whatever you stick into the Ethernet port of one radio comes out the Ethernet port of the opposite radio. And they have different ranges, different speeds, different frequencies, et cetera, et cetera. Lastly, the bottom row, we have serial devices. Whatever you put into the serial port of one radio comes out the serial port of the opposite radio. And of course, cellular modems, which are gaining in popularity. So that was just a quick introduction to let you know what we do. Now we're going to talk about some of the spectrum that we have coverage for. We make radios that go all the way down to 60 megahertz and all the way up to 5.8 gigahertz. And there's a variety of different reasons why you would use each radio in each specific frequency band. And I'll jump into that as we go on a little bit further. But this just gives you an idea that we cover all of the different frequency bands. So if you have an engineering company in California, for example, that is working on a project in Africa or in the Middle East, we most likely have a radio that can be utilized in that region. So this is what a complete radio system looks like. We have the radios themselves. Then we have the lightning arrestor or lightning diverter, which connects directly to the antenna connector in this example. Then we have the coax cable that allows you to mount the antenna someplace up high. Then we have the actual antenna itself, the radiating element that is typically mounted up on the roof or about as high as we can get it. And lastly, we have our DC power supply. So as a minimum, a radio system is going to consist of these 4 components right here. The power supplies being fairly common, you're going to find them all over the place, of course. So the bill of materials is, as a minimum, going to include the radio itself, or radio modem, as we sometimes call them, the lightning arrestor, the coax cable, and then the antenna itself. Okay, so that's what we deal with as a typical system there. And then sometimes we have some surge diverters on the inputs and the 4 to 20 inputs and things like that as well. Now the next thing is RF terminology, wavelength and frequency. I think most of you guys are engineers on the call, so I'm not really going to chat about this too much. That should be pretty straightforward. Next is the frequency spectrum that we operate on. And you probably heard these terminologies mentioned at some point in your careers. We deal with the VHF, UHF, and SHF. Those are by far the most common frequencies utilized for industrial communications today. So now I'd like to talk about a couple of different types of radios that the FCC permits us to use in the country and how they relate to spread spectrum. Spread spectrum is just a generic term that refers to a radio that uses a wide or large portion of the spectrum. And the FCC created some rules back in, I think it was the early 80s, for the 900 megahertz band, and they said you can make a radio that either uses direct sequence modulation, or you can make a radio that uses frequency hopping modulation. And they're called, direct sequence spread spectrum or frequency hopping spread spectrum radios. And they have characteristics that are quite opposite of one another. and ELPRO has been able to utilize these to our advantage. For example, the 905U-1 radio, the 915U2 radios, for example, those are frequency hopping radios because they don't require very high throughput. We're only sending 4 to 20 milliamp signals and contact closures back and forth, so we don't need throughputs in the megabits per second. And there's a number of advantages to that, is that frequency hoppers are generally less vulnerable to interference because they're changing frequency continuously. On the other hand, direct sequence radios have the opposite characteristics. They have much higher throughput in the range of megabits per second. And in fact, our 945U-E, our Ethernet pass-through modem, this radio is a direct sequence radio because of the requirement of high throughput. The 945 can do 54 megabits per second, so you can do things like wireless videos or wireless video cameras rather, and set them up for corporate networks because they have such high throughput. However, they are slightly more vulnerable to interference. And we're going to chat about the pros and cons of these two techniques in a couple of minutes here. So this is what a frequency hopper would look like on a spectrum analyzer if you looked across time and frequency. It randomly changes frequency over time, transmits the data, and if it does not get an acknowledgement back from the opposite radio, then it just retransmits that data on a different frequency, and thereby hops around and avoids interference. And you can have frequency hoppers on the 900 or the 2.4 gigahertz frequency bands. So here's how a frequency hopper deals with interference. If we had a blob of interference that blocked this portion of the spectrum, if this were occupying 10% of our 900 megahertz spectrum, then we would still have throughput on the other 90% of the radios. And if this blob of interference were to occupy 50% of the bandwidth, then the throughput would drop to 50%, but you would still have communications. It wouldn't be unless this blob of interference occupied this entire spectrum that we would finally lose communications. And that's what makes these frequency hopping radios so reliable. So that's one of the pitches for frequency hoppers. Very reliable radios. The FCC put a lot of thought into it. And but there's certain applications for it. And before I chat too much more about that, I'd like to talk about what factors affect the distance that you'll be able to get out of a radio. And the number one factor is going to be the frequency. As the frequency gets higher or increases, the distance decreases proportionately. So if we compare 900 megahertz to 2.4 gigahertz, all other factors being the same, like the same transmit power, the same receive sensitivity, etc., we would find that the 900 megahertz radio would have approximately 3 times the range of the 2.4 gigahertz radio because its frequency is about 3 times lower. And that applies right across the spectrum. The 450 megahertz radios will get even greater range. The 150 megahertz radios will get even greater range beyond that. The next factor is the receiver sensitivity. And the best way to think about that is it's like your ability to hear. How sensitive is your hearing? The more sensitive the hearing, the weaker the signal you'll be able to hear. And the receiver sensitivity is influenced by antenna gain and cable loss. The antennas boost the signal, the cables lose the signal. Then we have noise or interference. And it's just as though we're in a football stadium and if we were 100 yards apart, if there's nobody in the stadium, I could shout to you at the far end of the field and you could still hear me. But if we packed that stadium with 10,000 screaming fans, all of a sudden we would have a ton of background noise and it would suddenly be very difficult to hear you on the 100-yard line. Then we have transmitter power. The more power you have, the greater you're going to go. That's pretty straightforward. And transmitter power is also influenced by the antenna gain and the cable loss. Then we have the attenuation of the radio signals. And really what that boils down to is the density of molecules separating two antennas. So if we had two antennas that were in outer space where there's a complete vacuum and there is literally nothing there to absorb radio waves, then radio waves will travel for thousands of miles until they reach space dust or something to obstruct it, or a planet or something of that sort. Here on Earth, two antennas that have line of sight still have to travel through air molecules, which do attenuate radio waves. And as those molecules get more and more densely packed together, such as in a wood frame house or a concrete building, they attenuate radio waves more and more. So it really, the summary of that is it depends on the density of molecules separating the transmitter and receiver antennas. Okay, we're going to talk about the height of the antennas in a couple more minutes as well. But also, lastly, there's occasionally some other factors that will influence it, atmospheric, ground mineralization. Generally, these are going to be much, much smaller factors than the points all listed above. But that's what determines how far a radio is going to go. These are the factors that will influence it. Okay, now let's say we don't have line of sight. How do radio waves make it into your house, for example, for your cell phone? How do they make it around the corners of the house and inside the building? Well, there's several different techniques that radio waves use when they're traveling through the air that helps them scatter and spread. One of them is diffraction. Now, radio waves are a form of electromagnetic energy. They are just like light rays, except they are much lower in frequency than light is. So as you probably know, light is able to bend around a corner, and it does so by diffraction, which is the same technique that radio waves use. So when a radio wave hits the edge of a building or the peak of a mountain, some of those radio waves will bend around that corner, and they diffract around the corner. The other method of radio waves traveling around when there's no line of sight is scattering. A great example is when a radio wave passes through a tree. There's all kinds of leaves and branches at different angles, and the radio waves get scattered in all different directions. Now, of course, they lose some signal after these reflections or after penetrating through these objects, but some of the radio waves will still get through. Okay. Then we have, of course, our basic reflections. Radio waves reflect off all kinds of different surfaces. So this is another technique that they use as they travel through the air. Okay. Now, we chatted about the spread spectrum ISM bands, and ISM stands for Industrial Scientific Medical. That was their original name. That's what the FCC thought they would originally be used for. Now, of course, that's morphed into industrial and, it seems to me, consumer uses for these spread spectrum products. And they came out with the first ISM band in the 900 megahertz band in the early 80s. And that was very successful, but very quickly, lots and lots of users began to use that band, and it began to get a little bit crowded, so they came out with a 2.4 gigahertz band. And then later, several years later, they came out with a 5.8 gigahertz band. And there's a couple of fundamental differences between these frequency bands. The first one is because the frequency is different, the range that you will get with each frequency band is going to be quite different. So we would have the shortest range at the 5 gigahertz band because its frequency is quite high, medium range at the 2.4 gigahertz band, and then much greater range down in the 900 megahertz band. Now, the widths of each band, the 900 megahertz band is only 26 megahertz wide. So you can imagine with competition for spectrum, there's only a limited number of users that can all use that frequency band in the same area. Then we go to the 2.4 gigahertz band, and then it's 81 megahertz wide. So we can accommodate quite a few additional users there, depending on the radio type. keeping in mind that direct sequence spread spectrum radios occupy a much wider bandwidth than do frequency hoppers. So there's some give and take on that. Now 2.4 gigahertz is also used by microwave ovens because water absorbs RF energy very efficiently at that frequency. So that does make us realize that if we have an outdoor radio link over a fairly significant distance, we'll have to take into account rain fade and make sure that that radio signal is a little bit stronger than we would otherwise have. And then lastly, the 5 gigahertz band, it has the highest throughput capacity. In other words, the highest megabits per second. Because these frequency bands do not overlap one another, the 5 gigahertz channels, the Wi-Fi channels. So we can get higher throughput, but again, the range is going to be a little bit shorter in that frequency band. We used to say that relatively few products use this. That is changing as more and more consumer products are coming out in the 5 gigahertz band due to crowding in the 2.4 gigahertz band. So some different frequency bands there, each with slightly different characteristics. Now, as I mentioned, the lower the frequency, the better the object penetration. So if we had, in this example here, a half-inch sheet of drywall, the 900 megahertz radio is going to be able to penetrate it and pass through more sheets of drywall and accomplish greater distances than a 2.4 gigahertz radio would, all other factors being the same. Also, 2.4 gigahertz radios, the higher the frequency, they lose more energy after each reflection. So if we're in a refinery or a chemical plant and we've got all kinds of piping and tanks and structures around that the radio waves are going to bounce off of, we're going to get quite a bit greater range out of a 900 megahertz radio than a 2.4 gigahertz radio, all other factors like transmit power, receiver sensitivity, etc., all being the same. Okay, and we've covered some of the characteristics of the different frequency bands that are out there. I'd like to talk about antennas for a couple of minutes here and how they relate to the system. Now, what the antenna does is the antenna provides a 50 ohm impedance to the power amplifier on the radio. And it's just the same as your stereos and your speakers at home. The speakers usually come in 4 or 6 or 8 ohms. And then the power amplifier of your stereo has an output impedance of either 4 or 6 or 8 ohms. And so it's important that the impedance of the amplifier matches the impedance of the antenna. And that's what the antenna does. So at 900 megahertz, these antennas will provide a 50 ohm load at 900 megahertz. And that allows for the maximum power to be transferred out of the amplifier into the antenna and then out over the airways. So the antennas complete the circuit of a power amplifier in short summary. Now there's 2 types of antennas out there, and every other type of antenna that you see falls into one of these 2 categories. So we might say Yagi antennas typically look like this over on the right-hand side, but there's patch antennas, there's panel style antennas. They're all a glorified form of a Yagi directional antenna. Then we have omni antennas, which always look like a vertical staff, and some of them are quite small, others are quite large. They all have to be mounted vertically. And these omnidirectional antennas radiate in 360 degrees. So it's best to think of it like a lighthouse that has a rotating light that shoots over the horizon, but it rotates 360 degrees. So what we find is for omnidirectional antennas, we find them very successful in industrial plant environments where we have lots of reflections. And we don't necessarily know where the incoming radio wave, what direction it's going to be coming from because of all the reflections in a plant. We also have to use omnidirectional antennas as the master or base station antennas because we have to radiate out to remote sites in different directions. We also have to use Omni antennas for repeater sites, because repeater sites will also be shooting in different directions. The Yagi antennas shoot just in one specific direction, and so therefore we use them for remote sites only. Okay. So next is the installation also affects the radiation pattern and the performance of the antenna. So if you can see on the left, this would be your desired installation, where the antenna can now radiate 360 degrees. But if we mount it up against a wall, it's not going to shoot very far to the left because it's going to have to penetrate this wall surface. But it will have very strong propagation over to the right. And in some circumstances, some of that energy that gets propagated towards the wall will bounce off that wall and shoot over towards the right-hand side. So it's important that we don't mount antennas where we have obstructions immediately in front of them, because that will affect the radiation pattern. Okay, now with omnidirectional antennas, there's different sizes, and there's also different gain specifications. There's also different types. We've got dipole whips, which are going to be these little small ones up here. Then we have collinear antennas, which are much, much larger antennas. And then we have quarter wave, which stands for 1/4 of a wavelength whip antenna, which again are these little small guys down here. Now, as the gain of an antenna gets higher and higher, the size of the antenna gets physically larger. As well, the lower the frequency, the larger the antenna must be. Okay, and what gain is doing with the antenna is it's just taking the existing energy and it's focusing it in a very specific plane. So with these little tiny quarter wave whip antennas, these are going to radiate RF energy 360 degrees, both horizontally and vertically. So they'll radiate, their radiation pattern would look like a sphere. However, as soon as we get into a larger collinear antenna, it does not radiate much in RF straight up and straight down. It concentrates it to radiate it just along the horizon. So that's why it's important that we make sure that these Omni antennas, the large ones, are pointed vertically, because if they're tilted over on an angle, some of that energy will then be going up into outer space and the other energy will be going into the ground, which is typically not where we want it to go. Okay, so as the gain gets higher, the range or distance that the antenna can shoot also gets higher, because we're just concentrating that energy over a much narrower beam angle. Now with Yagi antennas, the principle is the same. This is showing two Yagi antennas that we sell. We have a 6-element, and the elements are the crossbars on these antennas here. And this antenna has a specification, the 900 megahertz version has a 9 dBi gain specification. The beam angle is approximately 45 degrees. So I can have this guy aimed 22.5 degrees to the left or to the right, and it's still within specification. As we get to a higher and higher gain, like our 9-element Yagi, which has a specification of 15 dBi gain, the beam angle gets narrower and narrower. In this case, it's still 35 degrees, so it's still pretty easy to aim. We don't have to take any great care, other than making sure we're reasonably comfortable we've got it within, 17.5 degrees to the left or to the right. So that's what these antennas do, is they just take the existing energy, they concentrate it into a specific direction, and in doing so accomplish greater and greater ranges. Okay, now as I was mentioning, as the gain spec for the antenna gets higher and higher, the antennas themselves get longer and longer, or taller and taller in the case of an Omni antenna. Now in this diagram, you would never mount these antennas like this. This was just done by the manufacturer just to illustrate a couple of different gains of antennas that they sell. So, and again, we can see these elements down here. The elements are the crossbars on these antennas here. So, and then of course, we get smaller and smaller antennas, the gain gets lower and lower, and the distance you'll be able to accomplish also gets lower and lower. Okay, then it also matters how you mount these Yagi antennas, if these crossbars are vertical or if they are horizontal. When the crossbars of a Yagi antenna are vertical, it means the radio waves have been vertically polarized. And what that means is that they just simply travel up and down in a sinusoidal fashion. Omnidirectional antennas, when they're pointed up and down, are always vertically polarized. So when we have a Yagi antenna shooting to an Omni antenna, we have to make sure the Yagi antenna is vertically polarized. Keeping in mind, you can mix and match antennas, so we can have Omni antennas shooting to Yagis or vice versa, any combination. And also, it's important, worth mentioning, that the distance that you can shoot with these two antennas would be the same as long as the gain specification is the same. So I'll get the same distance out of a 5 dB Yagi as I would out of a 5 dB Omni antenna. Okay, then we have the other option for mounting is horizontal polarization. Now this is not done very often because you can only have a Yagi antenna shooting to another Yagi antenna. The other issue that we run into in North America is snow buildup on the elements of the antenna. When the antenna is mounted in this fashion here, snow will accumulate on the antenna and it will change the shape of the antenna and therefore the radiation pattern. There is a way of getting around that, and that's by using a plastic or fiberglass radome surrounding this radiating metal element here. So that's one method, and the fiberglass or plastic radome keeps the snow off the radiating elements and therefore maintains performance. Now, of course, if you take this same Yagi antenna and you just rotate it 90 degrees so that it's now vertically polarized, no significant snow or ice accumulation is typically going to occur, except perhaps in the case of a fairly extreme ice storm. Okay. Now, one of the other concepts to be aware of is how high antennas have to be mounted above ground and how height must increase as the distance between two radios increases. And this is for a variety of different reasons. I'm going to elaborate a little bit more in a couple of minutes. But one of them is just simply curvature of the Earth. As the Earth, as you get farther and farther away, at some point you'll have Earth in between the two antennas. And of course, the more dense the molecules are separating two antennas, the shorter the range is going to be. So we have to avoid shooting through Earth. And one way to do that is to elevate the antennas. But there's another reason, and that's called the Fresnel zone, which is what we, some of the science behind radio propagation. And I'll show you that in just a couple of minutes here. But for now, the rules of thumb that you can use, and these are examples from a 900 megahertz radio. If you had terrain that was as flat as a soccer field for a 1 mile distance, you can have each antenna just 14 feet above ground. If we had a 5 mile stretch of distance as flat as a soccer field, that entire 5 miles, we could have each antenna 34 feet above ground. And if we wanted to go 15 miles, we would have to get that antenna all the way up to 81 feet above ground. Now, in the real world, we've got houses and trees, and the terrain is never as flat as a soccer field for any significant stretch. So in reality, antenna heights will need to be higher than these ones, but these are the theoretical minimum antenna heights for 900 megahertz radios. So one of the things to keep in mind is if you have a customer and he looks at the data sheet of one of our radios, for example, our 915U2 wireless I/O radio, it quotes a maximum range of 20 miles. And yes, you can go 20 miles with that radio, except that you're going to have it very tall above ground. So you might have to have that antenna 120 feet above ground. So what's going to happen is the cost of building a tower is probably going to exceed all of your other costs of buying the radio and the cable and the hardware and the installation and all that sort of stuff. So at that point, we would say, is there a repeater site that we can use that has power and perhaps even has line of sight to the two other sites? So before we start thinking about 20-mile radio lengths or even 15-mile radio lengths, we have to realize that we're going to have to build a tower or have an existing structure that we can mount the antenna to before those distances become practical. And if they aren't practical, then let's look at repeater sites to accomplish those distances. The other factor to be aware of is other antennas. So when we climb up onto the roof of a building, we'll often see a couple of our other antennas also mounted on that roof to give good propagation. So we have to stay away from other antennas. Generally 10 feet vertically or 100 feet horizontally is sort of a rule of thumb, but I have a chart that shows you more specifically what distances. And it's important that we stay out of the radiation path of another antenna. Like if we have a Yagi antenna on that same roof of a building, it's important that we don't mount our antenna right in front of that Yagi antenna, because that antenna would just be blasting right into our receiver's amplifier. Okay, so here's what the antenna separation requirements look like. Now, you either require vertical separation or horizontal separation. We don't have to do both. And as you can see from these distances, vertical separation is 10 times more effective than horizontal separation is. So usually, if we have a tower or a pole, we want to make sure the antennas are above or below each other, not on the same horizontal plane. And the distance, the separation requirement, it varies by distance as well. Or I'm sorry, my apologies there. It varies by frequency as well. So if we look at this chart here and we have two 2.4 gigahertz radios, they only have to be 1.5 meters vertically separated from one another. And if we had a 2.4 gigahertz radio and a 900 megahertz radio, they would have to be 2.3 meters vertically separated from one another. So these are guidelines, just enough to keep you out of trouble and make sure your radio links work reliably and that we don't have to worry about noise from other antennas. Okay, so then I wanted to talk about some typical ranges that you'll be able to get with our radios, in the real world. And now I'm going to start with a 900 megahertz frequency hopping spread spectrum 1 watt radio. So that covers our 905U-1 radios, the 905UG, the 915U2. Covers most of our 900 megahertz radios with the exception of the 945U-E. That's the only one it does not cover. So if we have our CFD 890EL, this is an antenna that's 16 inches tall, comes with 16 feet of coax cable. We mount it 10 feet above ground. We have a densely obstructed path, like lots of trees, houses, definitely no line of sight. Over 1,000-foot distance, we can do it quite easily. If the obstructions are a little bit lighter, we could go approximately 2,000 feet. Again, if we just bump that antenna height up just a little bit further. At 5,000 feet, we can still transmit through some light obstructions, but we better boost that antenna gain to a 9 dBi Yagi. As well, we're going to have to increase that antenna height, so I factored in some extra cable, a 33-foot length of coax cable. And of course, we get longer and longer distances. At 10,000 feet or roughly 2 miles, that's the cutoff point where we have to have line of sight. Anything beyond 2 miles, each antenna has to be able to see each other. And of course, we can go some longer distances, like up to 5 miles, as long as we have line of sight. The antennas need to be approximately 50 feet above ground now. So we specify some longer cable and off we go. So those are some real world numbers that we've dealt with before. Now moving to our 945U-E, this is our high-speed Ethernet modem. It is a direct sequence spread spectrum. Sorry, this is a typo up here. This should say DSSS. This radio has 630 milliwatts of transmit power, and these are some of the distances you'll be able to accomplish with it. Generally, with this radio here, at about 1,500 feet is the cutoff point where we need to have line of sight. So just gives you some ideas as to what we can do. Now, I do want to give you one example. We did a project with an electrical utility. They were installing smart meters on all of their residential houses throughout the city. And these smart meters used a 900 megahertz frequency hopper to get to a gateway. And they wanted to connect our 945U-E to the gateway radios to do the long distance backhaul to their substation or to their control rooms. And so this was an example where we had a 1 watt 900 megahertz frequency hopping antenna mounted on the same telephone pole as this direct sequence spread spectrum radio, and both radios were able to operate successfully because we separated those antennas by about 10 feet vertically on that telephone pole. So we can have multiple radios all operating in the same area as long as we separate the antennas accordingly. Okay, moving on to the 2.4 gigahertz band. I've used the 245U-E as an example here. It is also a direct sequence spread spectrum radio with 630 milliwatts of transmit power. And these are the distances that are typically able to be accomplished here. And as you can see, as the distance gets greater and greater, we're either going to require line of sight, or if we boost that antenna gain and we go up to these higher gain antennas, we can tolerate very light obstructions, but practical distances are going to be, less than 1.5 miles. Okay, then we go up to 5 gigahertz, and now we're also looking at a direct sequence spread spectrum radio, and you can see the distances get even shorter here. If we boost these antenna gains, we can get some pretty high distances, but being conservative, I've just given you some ones that are reasonably practical that aren't going to require too much specialty expertise to install. Then lastly, we drop down to a 450 megahertz frequency band, and these are licensed radios. So in the 450 megahertz band, we have to contact FCC and we have to get a license to operate it, and they will give you a license for a certain geographic area. And they'll usually give you up to 5 watts of transmit power. And so because the frequency is lower and the power is higher, we can go a lot greater distances with these 450 megahertz radios. So it isn't until we get past 3 miles that we begin to require a line of sight for these radios here. So we can share all this information with you, so you don't have to necessarily write it down. And again, these are guidelines here, so it will depend exactly how dense are these obstructions over this 2,000 foot distance. But again, these are going to be typical numbers here. Okay, so one of the next things to think about is EIRP, which stands for the effective isotropic radiated power. And this is a limitation that the FCC puts on your radios. Now, if you get a licensed radio, like a 450 megahertz licensed radio, they'll probably just specify a certain EIRP, maybe 40 dBm or something like that. And that is a combination of the transmitter power plus the antenna gain, subtracting the coaxial cable losses. And the reason FCC puts a limit on the EIRP is so that you can't put an absolutely gigantic antenna on your transmitter and then potentially generate interference to users that could be hundreds of miles away. So that means that it only applies to transmitters or transceivers. Receive-only antennas can be as large as needed because a receiver does not generate an interference, only a transmitter does. So we can also convert 1 watt into dBm, And this is what it's equal to. 1 watt is equal to 30 dBm. And we use dBm in the math because the power deals in an exponential format. So it's very difficult to really do calculations using watts. Much, much easier to do calculations in dBm. Okay, so the chart on the right-hand side shows power in dBm, what it correlates to power in watts. So you can see it's an exponential relationship here, and the numbers with the dBm, they just go up linearly, and they're much, much easier to do the calculations. So when we're doing a radio installation, you'll see talk of RSSI, and that stands for Received Signal Strength Indication. And for example, a good signal strength would be about -70 dBm. And of course that correlates, you can see that's off the chart in very, very low power levels, which goes to tell you that the receiver on board the radios, on board these radios is very, very sensitive. And that's why we always have a lightning arrestor connecting to the antenna. Because that receiver is by far the most sensitive piece of circuitry inside the radio. So that's why we always have lightning arrestors for radios, is because the receivers are very, very sensitive. So now in the data sheet of a radio, it's going to tell you what the threshold of reception is. A typical threshold of reception is going to be -110 dB. So that is the weakest that the signal can be, and reception still function. But of course, we want our signal to be a lot stronger than just the threshold of reception, because we want to allow for things like equipment to degrade over time, or a heavy snowstorm to come in and act as an additional obstruction, or for foliage, trees and bushes to grow taller and taller and taller over the years and get thicker and thicker. So this is why we actually want the signal strength to be much stronger. Typically we want at least a 20 decibel fade margin. So we would want to have our signal strength at -90 dBm as a minimum. Now here's where the calculations, here's how the calculations work, is we start with the transmitter on the left, and we have 1 watt of power, which is equal to 30 dBm. Then we have your transmitter coax cable. And let's see, for the length of the cable, if we lose 4 dB, so 30 dBm minus 4 dB is 26 dBm. Then we have our antenna gain. Let's say we're using a 5 dB gain, so 26 plus 5 is 31. Then let's say we lose some signal over the distance. Say we lose -100 dB of signal, just air molecules, trees, houses, bushes, all that sort of thing. So we were at, let's see, that was 20, we were at plus 31 minus 100 is, boy, I hate doing this math out loud because I'm always worried I'll make a mistake here. But let's see, that's going to be, I think it's -60, what is that, -69? Yep. Okay, so we're at -69. So then if we have a antenna that has 5 dB gain, so -69 plus 5 is going to be -64. And then if we lose 6 dB in that signal, -64 minus 6 dB gives us our received signal strength of -70 dBm. So that's how these calculations all work, is antennas add to the signal, cables lose the signal, and we start with a baseline, which is your transmit power of your sending radio. So these are how the calculations work. If we talk about dB numbers, that's what we're referring to here. Okay, now there's all kinds of different types of coax cable, but they're all fundamentally the same. They have a center conductor, and then they have a braided shield going around the center conductor, and the shield prevents RF energy from escaping out of that center conductor. Now, generally, the thicker the cable, the lower the losses per foot will be. However, the thicker the cable, it's quite a bit more expensive. And of course, the thicker the cable, the wider the bending radius is, so it's not quite as easy to work with as thinner cable is. So it can be something to keep in mind for the installer. Okay, then let's see here. Okay, then the next thing to think about is wrapping the antenna connections. So where the cable connects to the antenna, high up on your pole, you're going to have to make sure that is waterproof. Because that is a threaded type connection, one end can spin freely, and therefore there is a gap where water or moisture could get in. So it's very important that we weatherproof these the coax connections. Everything has to be weather tight. Should be done the day you're installing it. Try not to come back a second or third day later, because that gives an opportunity for rain or moisture to get in. And believe me, if it has been raining outside, water will get inside that coax cable. Okay, then we have our lightning arresters. This particular style of lightning arrestor, the one we're showing right here, it actually connects directly to the antenna connector on the radio itself, and then the coax cable connects directly to this one here. There's different styles of lightning arresters. A fairly common alternate style is the bulkhead mount, where you have a metal electrical enclosure, and the lightning arrestor here just screws through a hole that you drill in the bottom of the enclosure, and then it has a nut on the top side to hold it in place. And then inside the electrical enclosure, we have a jumper wire that would go from this lightning arrestor to the antenna. So there's a few different styles of lightning arrestor. They all perform the same function, which is to keep surges or transients out of the radio here. Okay, now I wanted to chat for a couple of minutes about the Fresnel zone, and just to let you know how we're doing on time. I see we've got about 7 or 8 minutes to go, and that should have us wrapped up at the top of the hour. The Fresnel zone is an area of free space between two antennas that looks like a stretched football, and this three-dimensional zone has to be 60% clear of obstructions for successful propagation. So that means that we can have some trees or buildings protruding into some part of this Fresnel zone. Just 60% of this three-dimensional stretched football has to be clear of obstructions for successful propagation. So when we have line of sight from one antenna to another, we in fact require just a little bit more than line of sight from each antenna. So it's best if you've got just barely line of sight between two antennas, if you can raise one or both antennas a little bit taller so that we have good clear line of sight, and that also provides us with clearance for this Fresnel zone. Now there's a formula for calculating how big the Fresnel zone is. It changes with frequency and distance, but this is the formulation, this is the math behind all those calculations that cellular companies are doing or two-way radio companies are doing to figure out radio penetration. Or this is also what we do for our SCADA networks to calculate how high each antenna needs to be above ground. Now, it will change as frequency changes. I don't think it's too important to kind of memorize this kind of information. Just to know that we have a software program that can calculate this for us. So, and here we go, just showing the rest of the chart here. As the distances get longer and longer, the Fresnel zone gets larger and larger, which is why these antennas need to be higher and higher above ground. Okay, so if you had a long distance radio link, like say anything beyond 1 or 2 miles, anything less than 1 or 2 miles should be tested with a demo kit, like with a live pair of radios. But If you're talking about a 5 or 6 mile radio link, you might not be able to elevate each antenna high enough to be able to test that radio link. And you might have some questions about exactly how high do we have to mount these antennas. Well, if you send me the GPS coordinates for the transmitter and receiver locations, I can run them through a software program that I have. And this program will download the topographical data for the area from the U.S. Geological Service website. It will also download these terrain coverage files here. And, oh, sorry, I did that by mistake. The terrain coverage shows is a map of what sort of foliage is in the path. And that factors into these Fresnel zone calculations. So what this survey will tell us is how high each antenna needs to be able to get suitable reception. And it's a very powerful, very useful studies. I have that program. We do charge for that as a service, but if it's a minimal number of sites and if it's something I can do very quickly, oftentimes I'll do so free of charge. I'll just request that you buy me a beer the next time I come to visit. But we can provide a complete system design. So we can tell you from each location to the next one, how strong we estimate the signal to be, what length of cable you're going to need, how high above ground that antenna needs to be mounted to have successful propagation. So we can help you with a complete design of a system by using our path loss software program. Okay, so we're just wrapping things up here. These are the tips for best performance with a radio system is line of sight when possible from antenna to antenna. Keep the antennas outside of the electrical enclosure because that will minimize the number of obstructions. And oftentimes those electrical enclosures are made out of metal, and metals will block radio waves completely. Keep the antenna away from noise sources, which really is other antennas. That's primarily the dominant source of other RF noise. Keep the antennas as high as possible above ground for best propagation. Keep the coax cable as short as possible because we lose a lot of signal in that cable. And then make sure we ground the radio to the equipment, and we have proper grounding of all of the equipment in the enclosure. And as a general rule of thumb, we also recommend you ground any other noisy equipment like VFDs or sometimes even PLCs might need some grounding as well. And that pretty much wraps things up. This graphic here just kind of gives you an idea as to where radios are being used. And these days, it's just about everywhere. We have done literally thousands and thousands of different applications. I believe the company has over 500,000 radios installed today, and literally all over the world. I believe we have installed our radios in over 80 different countries. So that pretty much concludes things. Guys, thanks for listening.